Okay, let's start the second round of this fight. So I want to ask the opponent, you have 1 minute to pick up probably and challenge the reporter. Willing ball. Willing ball. 15. Okay, problem number 15. Reporter you have 1 minute to decide. Accept. Problem has been accepted. So reporter, you have 5 minutes to prepare your presentation. So also, please write down the name of your presenter on the whiteboard.
Good morning, everyone. I'm going to give a presentation about problem 15, welding flow. This is what we'll mainly discuss here. So let's start first on the introduction of the problem. When we can hear the sound of the frequency when we strike against the board, the frequency lowers when still water is present. What's interesting is when the water starts moving. Apart from the further decreasing end, a characteristic sound can be heard. This presentation utilizes these literatures to help develop some basic understanding of the problem. But before going straight into this topic, we have a few proposals that can help us break down this problem more easily. First, we divide all possible variables into two sections, setting up corresponding experiments to prove validity. Second, we discuss more notable things when performing these experiments, later shown, which can improve convenience while not affecting the results. Let's first start with some possible non-affecting variables. Making sure that these variables doesn't affect the results can help us refine our experiment models later on, as we didn't have to measure all the parameters then. Variables which falls into this category includes the solution's mass, which we'll see later in the discussion section, place to apply the force, meaning where we're going to hit the ball for it to make sounds. Relative position is just a quantitative description of where we're going to record the sounds, and we'll discuss the magnitude of the force at last. Now for some possible affecting variables. We tend to describe the cause of delta F and make relational expressions if possible. We're not going to detail like the last slide, as we'll have more time discussing this later on. Now for some notable things when we're performing experiments. We'll start by defining what a standard state means throughout the presentation. A standard state is a state where applying the force doesn't greatly affect the outcome, which is F in this case. For example, it's absolutely okay when the water depth is 4 centimeters tall, but it could be troublesome when the stir bar is working about 1200 RPM under this condition, because water can splash everywhere and it's hard to record the mean frequency. Talking about the things to note in this experiment, now this is some actions for others to reproduce our experiments. These actions aren't necessary, as talked before, but same as above, it minimally disrupts the outcome and can maintain convenience when recording the F. Analyzing data is also a part of our experiments. We use two different programs by feedbacks, one for determining main frequency and one for determining the exact number of F. But how can we determine the delta F of a complex variable? For example, is that of viscosity and density. There are two variables that are generally hard to separate from each other. So it can be sometimes confusing and hard to separate. So we simply take density as a one only variable and here, and keep the delta F and keep the viscosity change in a relatively small range, so we can consider density as the only variable here. By literature, we can suggest an expression of natural frequency, F, as shown in this equation right here. We will not go deep into the calculations here, but bear in mind that this equation might be useful later on. And now it's finally time for some experiments. As above, we'll divide this section into possible non-affecting variables and affecting variables. We notice that different striking point. Let's start with the place of applied force. This is a relatively easy experiment to do because we just make marks here and strike each position and record the relative F. We notice that different striking point does not have a significant impact on the frequency, which is great because we now can strike wherever we want without having to worry that the F might change. And it's interesting when we strike and the striking point is very close to the top of the ball because then we'll hear a very sharp sound. It's sometimes hard to reproduce and does not change with the depth of the water. So by now we'll consider it irrelevant. Moving on to the relative position of a striking point, we place two same procedures as before, but with different recording precision, like here. As we guessed before, place to record does not have a significant impact on F. What's more beside the result is that we can notice a cyclical change of a frequency F when recording. We're not jumping into conclusions right away, so let's move on for now. Because we can't apply exact amount of force at a time, we record the magnitude of force by using a single pendulum with a release at angle theta. Although as the graph here, E isn't in linear expression as of theta, but we can still compare to get the exact amount of force applied to the ball. Another point is that we notice a regular pattern appearing when theta is greater than 30 degrees. This can be due to the force from creating surface waves, where there should be none because the water is still, which is not great. So we simply just abandon the data altogether. Apart from all this other stuff, let's not forget that delta F, that F remains constant throughout this process. So the magnitude of force just doesn't matter in short. Moving on to the second part of the experiment, we first discussed different vibrational wave patterns of the water and its impact on F. One notable thing is that when we use F0, we're referring to a frequency of a water droplets dropping from a volumetric pipette, and by F1, means the frequency of a surbar. Comparing these two waves of generating waves, we can see that F0 has a greater impact on F, and also more convenient to measure. It's not good to keep all the questions unanswered, so now let's go through a few of them. Remember in experiment 1-3, we wondered, what's also cyclical? It should be obvious that the waves we're generating is cyclical, but it's also sending cyclical pressure on the side of a ball, causing cyclical delta F when recording. This may also be responsible for the characteristic sound we hear when the water is moving. Now let's discuss the influence of F caused by F0 specifically, because as we mentioned later, F0 is easier to measure. After working out the data, we figured that delta F and F0 can approximate to a linear expression, like this equation right here. This is an important step because we simply assume that there are two variables that obey y equals ax times to the power of b. And we can confirm this calculation by looking at the regression coefficient, R here. Higher R suggests that we are indeed doing the right approximation, and that's exactly the case here. Now for the water's depth, we set up different water's depth and L and record different corresponding F, and the rest as above. Same as before, we can approximate the relationship between delta F and L as a variable here, and we get a relatively high R, means we're doing the right approximation. Lastly, we choose different bowls, or rather beakers in this case, to create different width for the waste to present. It's impossible to find two same bowls of the exact composition, so we simply take beakers with different capacities to reduce this interference. Notice we only include 2 points here, but that's because unfortunately there are only 2 kinds of feature available at the time, so the relational expression might be misleading at this point. Although it might not be the most accurate expression ever, we still learn to use approximating to help us analyze the data we get. It's quite inappropriate to leave this experiment as is, so we tried explaining the change in a different approach. We suggest a proportional constant z, which equals the left of the equation divided by the right of the equation. It should be 1 in ideal container, but for the real situation now, it might not be always that case. The chart here shows documentary of different parameters at different containers. Just remember that by comparing the value of z, we can see which kind of balls that fit the equation better and which one doesn't. And now we talk about the conclusions. For this relational expression from 2, 3, we suggest that increased pressure causes the ball to be oppressed, lowering the natural frequency f. This can further extend to a speculation that any variables that cause the change in the depth should have the same result that can be expressed as an equation above. Talking about the delta f caused by f0, we infer that the vibrational wave can have pressure applied to a side, further decreasing. As mentioned above, any change that causes the surface wave to occur should have the same effect that can be expressed in the equation above. We didn't dive deep into the effect of delta f caused by f1, and that's because it has such a small influence of the system that it cannot be measured when f is smaller, when f1 is between 0 and 1200 RPM. Such drastic stirring makes the water splash everywhere, and it's generally not possible to measure the f. We therefore propose that surface waves are the main reason of delta f, and it was more convenient to observe delta f when experimenting. And lastly, though we just said that it is not possible to work out the relational expression between delta f and f1, it is still achievable in theory. It can be a way to predict experiments so we can get a general concept of a variable that we are working with.
Okay, time's up. Almost to take some short questions.
Okay. Do you in the first when you talk about setup, you said it's hard to maintain the frequency. Do you maintain the frequency?
Maintain
The water frequency. When you hit the ball, the water will flow. And do you maintain its frequency?
the frequency.
The water. Like
the frequency of the water, right?
Yes.
The frequency of the water, in theory, it should change over time, but in our observation, the change is very slight. The change is very slight, and it cannot be measured.
Oh, okay. Is the ball with the same force? Like do you hit the ball at the same force?
In one of our experiments, we talked about the influence of the magnitude of force applied on the ball, and when the magnitude of force is getting bigger, we didn't see any change in F, which means that the magnitude of force applied onto the ball doesn't affect the F overall.
Okay. Is the height of the water affect this data?
I believe we have a relational expression here. And as you can see, the L means the depth of the water here, and delta F means the change in frequency.
I remember you have a page talking about there are only 2 sides of them. Just you only have 2 balls on the experiment, and
This is
yes, and can you repeat again when we are in discussion part?
when we're in this slide.
When after the discussion, can we talk about that?
discussion later on. Following this slide.
Time's up. So Tony, you have 3 minutes to present your presentation. Okay, I'm going to start. 跳下一个。
short, let's talk about problem statement. When you strike the side of a metal ball containing some water, you can hear the characteristics and the sound changes when the water in the ball is moving. Explain and investigate the phenomenon. And as to the theory, they talk about a lot of equation, and I think it's their pros. And as to their data, I'm quite curious about is that the ideal or the experiment? Like is the way the curve of the graph is kind of ideal, and I'm quite not sure if it's ideal or for the real experiment. And pros and suggestions. I think they have a good work on the software and they track the experiment, and they create some formula. And as to suggestions, I think I think the ball's angle maybe is one of the parameters. Like is the shape of the ball affects the data, and the area to hit. Like you use the hand to hit, right? And you use something to hit, and I think the area you hit might change the numbers.
So, time's up. So let's move to the next stage. We can start the discussion.
So why are there only two balls? Two balls in that experiment.
Because as we mentioned in the experimental setup, we couldn't find three balls with the exact same composition, and the composition of a ball really is an affecting parameter, and we can quantify the change in delta F by this parameter. So we simply assume that the two beakers we find on the exact same parameter, and the only difference in them is the width of a ball. And
But why? I want to know why.
why about what?
Why about there's only two? Because you assume it, right? But why you can just assume two of them instead of why there are three data?
I get what you're saying. Because
Keep going.
and the point, third point is supposed to be right here. And when we are talking about the change of F due to the R, we are assuming that all of the other parameters doesn't change. So in short, the third point right here, it does not include in this experiment because we're talking about this specific composition of a beaker that makes the delta F change in this way.
Okay, so are there another parameter to this because this is one of the parameters.
Yes.
Are there another parameter just like what I said, like the angle of the ball, the shape of the ball?
Yes. I didn't include this in my report, but we did consider this as a possible affecting variable. And as in experiment, we couldn't find a perfectly round shape of ball.
Oh, you mean you find a lot of shape of balls, but what did you do about this?
We simply choose the ones that they are like this shape. I don't know how to describe this in English, but it's like this. But why do we choose that? That is because that the table is supposed to be
it's flat.
And so when the ball is not when the bottom of the ball is not flat, it will shake, it will move around when we strike it, and making the delta F hard to reproduce.
But if there's flat one, but the shape of it is like a round instead of just like you can do another experiment. Like this is a straight line, and you can do a curved line to make it more symmetrical.
Yes, it did. So
This is my suggestion.
yes, I know what you mean. So by using this experiment, we can learn how to break down the question one by one. But by the shape of a ball, people may think about 100 different variables, but we today choose one of them to discuss because we think that's the one simple way of judging how delta F will change because of one of the variables of a ball. We did indeed can choose another variable to change, but unfortunately, like I said before, we just doesn't have that much of a ball to do the experiment.
And there's another question that the ball is like when the ball hit on the container, there are some areas, and when is the area affects the force?
And we did, when we consider the magnitude of a force applied on the ball, let's go back to the presentation here. Okay. Here, we consider this coefficient right here because we notice that the striking ball did bounce back after striking the ball, and we assume that no other work is wasted in this process. So, sorry, what's the question again? I forgot.
The area of the ball hitting on the container on the ball.
This is indeed something that we didn't take into account with, but I believe that as long as we choose the smallest possible striking thing we can get, we do indeed will get the similar results.
Okay, and I'm kind of curious about that graph. Is the graph about your equation, or the graph about the experiment, or the software you use to track?
That makes sense. Let me explain. So this is a graph about E to theta, because we know that E has an equation of theta, and we can see that this is not a linear expression. It's quite inconvenient, but because we can measure the angle of theta, we know exactly the amount of force that we put on the ball, as we can put in this equation to get one. So we compare what does this sentence here? It simply means that while doing all this, we're also collecting the data of F, and we notice that delta F is 0.
Wait. Is that graph your equation or the experiment?
And by this experiment, we can derive this equation, and this graph here is simply just the E.
And what about the experiment graph?
Experiment graph is quite boring because you just see F as a straight line. So when we compare our delta F to delta theta to delta F, we can see that the change in theta does not affect F. So what I'm trying to say here is the amount of force acting upon the ball does not affect the change, does not affect F, because while the amount of force applied to it is increasing, the F doesn't do anything. It remains constant.
And do you use the small angle pendulum formula?
Yes, I do indeed use the approximation of that.
Why can you use that? Like it's a small angle to small. It's a small. This is
Small angle approximation, right?
Yes.
I do believe that. Are you referring to this? And are you referring to that when I put theta that's greater than 30 degrees in that, I'll get a different result than in reality?
Yes.
I do believe that is not as quite important as you may think, because what I'm trying to say here is when you strike the ball hard enough, you'll create surface wave while the water is supposed to be still, and that's not good because we do take into account that the surface wave does matter in F, but that's not the case here. We're trying to describe the delta F caused by the magnitude of force, not caused by the surface waves. So we try to do this experiment while maintaining theta as small as possible, so that we can measure the delta F while the approximation isn't too deviating from the reality.
Is there any page that talks about the pressure?
Pressure. Oh yes, I didn't talk about that so much, but we try to derive. We try to derive the pressure applied on the side and pressure applied on the bottom, because we think that those will have different impact on F. Therefore different expressions for each of them. So. So we consider why do we put mass as an why do we put mass as a non-affecting variable? Because consider this, we use this is just something that I talked about earlier, and we can use the solutions with different densities to verify. And how will we make those two solutions? And one of the solution that we're making is like just water, and the density of water is 1, right? So we make a solution of water and a solution with a density that's smaller than 1, but with solids that's so small that it doesn't contribute any pressure onto the side, but only the bottom. And we try to maintain the mass of these two solutions the same. But while
I'm sorry, the time's up. So, opponent, please summarize your discussion.
We discussed about the pressure and some questions like is the graph reality or is it an ideal? And he said because delta F equals delta zeta, so it doesn't matters. And just the ideal is the experiment. And I think I ignored a question, is that he said density is the only parameter.
Okay, so the question from the viewer.
Okay, so I have 3 questions for the reporter, for both. I want to ask both. What do you think the Bernoulli equation can be implemented in this?
Bernoulli equation. Oh, okay. So, can we switch back to the question? Well, theoretically calculating the delta F caused by F1, we did indeed use the equation of Bernoulli equation.
Oh, that's okay. I want to ask you about what do you think is the most important factor in this experiment?
Most important factor.
For both.
It's important factor. I didn't think that.
Just a short answer.
Just a straight answer. Oh, I think that I do think that water's depth matters the most, because by exponential power is like 3.4, while others are like 1 or 0.8.
Okay, thank you.
I think it's about
Just does stress answer mean?
Force, because he said about the delta F equals,
You mean the striking force?
yes, the striking force.
I think the most important factor is the volume, because volume will affect the pressure, and the pressure will affect the vibration mode. So. And what do you think the same radius will affect the, in the same radius, what different height have the frequency? Different height of water.
Sorry, can you repeat your question?
If the tank is in the same radius, what do you think the different height of water will impact the frequency?
While we discuss the change, while we discuss the delta F caused by L, we simply assume that all other parameters doesn't matter. So we assume that there's two different water solution with different height, but their width is the same. So
Do you consider the pressure will affect this phenomenon?
yes, indeed. And in fact, I was just talking about it earlier. So, the pressure on we try to, as what we have been over, I was trying to describe the change of F by deriving the pressure into pressure on the side and the pressure on the bottom. I try to derive these two as different parameters because I thought that they maybe have different impact on F, just like what we did on F0 and F1.
Thank you.
Okay, thumbs up. Reviewer, you have 2 minutes to prepare your presentation. Reviewer, please take the floor.
Hi, I'm reviewer from Maria Tech. So this is the problem statement. It talks about the changing sound that emits from a book. And there's an overview from reporter's presentation. First, the observation, they talk about the standard state. And the experiment method, they compare about the vibration pattern of the waves and change the sign of the ball and water and back and forth. And the data analysis is mostly from feedbacks. And their conclusion is that waves can press the side and lower the frequency, and hitting force doesn't matter. And here's the pros and cons of the reporter. For pros, they have tons of experiments and have clear charts with clear results. But for the cons, they lack of main focuses, and most importantly, the lack of patience numbers, which for me hard to find the chart I want to find. And I think they lack of experiment results, since some results is like lack of data. And here are pros and cons for opponent. Pros, they point out missed points from the reporter, like they give a lot of new sites of the experiments, and they clarify the definition of small angle pendulum. And some cons is that I think they keep on catching the segment of the reporter, and there's few unconstructed questions. And here are the discussion review. The opponent have asked, why were there only 2 data on the size of the ball, which reviewer for me also curious about. And they said that they cannot find 3 balls with the same composition. So we can assume that they are the ball. The balls are the same. And the opponent asks, there are some certain areas where the object hit the balls, but it affects the results. And the reporter said that they consider the energy loss in the process, but didn't consider the energy. And for the reviewer's questions, we asked about what's the main factor of this experiment, and the opponent said that the stretching force is the main focus, and the reporter said that the water depth is the main focus. And for the reviewer, we believe that volume of the ball is the main factor because it will affect the pressure that added on the side of the ball, and that will additionally affect the sound limit. And we have asked, while the same radius of the ball, how different height affect the frequency. And we also asked that, do you think the pressure will affect this phenomenon? And they have answered that they have considered the pressure of the bottom of the ball and the side of the ball. But for the reviewer, we only consider we think that the pressure added on the side of the ball will affect the frequency the most, since the pressure, yeah. And this is my review, thank you.
Okay, thank you. Concluding remarks from the reporter.
So let's make a conclusion here. By dividing those parameters that both the opponent and the reviewer asked, we have successfully clarified that what are the non-affecting variables and which there are affecting variables. And this can help us clarify which actually causes delta F to change and help us break down those complex variables one by one. And like I said in the presentation, when we consider a complex variable like the ball size or the ball's composition, we simply just choose to reduce it to a minimum. Choose to reduce it to a minimum so that it minimally disrupts the results that we get, or we break those down one by one and try to find some things that only affect one of the variables that we can talk about. And so that's also, I think, one of the ways that we can break down this problem more easily. Thanks.
Okay, thank you. So, question from the
So the problem is that when you strike the side of a metal ball, so what material there is?
I was using a wooden stick, and I missed the point when I was talking about the actions to take when we were doing the experiment. Is that when we strike the ball with our fingers, it did indeed make the same sound, but when using the fingers, we noticed that sometimes we hit the ball and the fingers leaves quickly like this. But sometimes when we hit the ball, the finger sticks on it and doesn't leave. And those makes different results. So we simply.
If you consider different material ball.
I mean when using the same ball, like the glass ball in the picture.
Using glass ball. And you consider does it matter if you change the material, metal or?
Yes, I did say that in the composition, because I do consider composition as one of our variables here, but it contains way too many complex equationing variables at a time, which makes it a very complex topic to talk about. So we, by the conclusion I just made it, we simply takes the balls with us, with absolute, with most, we want the balls to be the same as possible.
About the material of bulk,
The material.
okay. Metal or glass?
I didn't ask this about. I didn't ask this question.
I think the material is the main point to consider because different material have different natural frequency, and the natural frequency will additionally affect the frequency that the ball emits. So, personally in my experiment, I standard all the material. So, yeah. So.
Okay, please.
Okay, also about the initial problem. The problem say the sound changes when the water in the bowl is moving, right? So what mean the water is moving? What's the meaning of water is moving? Could you shortly explain what this means?
In one of our experiments, we describe the delta F caused by the different vibrational pattern because we observed that while hitting
I mean, what's the meaning of water is moving? How the water moving?
yes, of course, answer this question. So, while we drip water into different places of a bowl, we can observe different vibrational patterns, and that's the meaning of the water is moving. The water is making surface wave or the waves inside, and that's making the water. That's
You mean the moving, meaning the water has some weight?
waves and yes, and I think I will consider that as the main point as a main factor of affecting the frequency F.
Opponent? What's the meaning of moving? How the water moving?
I'm not sure about. I'm not sure about this.
So, in my experiment, we measure the water is still and moving. So when it's still, we don't manually move the ball. But when it's moving, we manually move the ball. And when we look at the spectrum, we can see that when the water is still, we will have an obvious high point of the frequency, you'll have a most loud sound then we'll take that frequency But when the water is moving, we'll have many different obvious frequency
So
in the spectrum.
the moving means the water is steering.
Oh yeah, rotating.
Okay.
Okay, I want to ask some short questions. So from you, do you recall your experiment? Recall the sound? What you heard? Do you recall?
Record, yes,
Okay.
it's my.
Then you got how many notes? How many frequencies? Your analysis?
It's
One
not,
frequency or several frequencies?
we do observe two main frequency at a time.
Okay, now I want to ask my question. If you got a ball, it's empty, and fill half of water or some liquid, what frequency difference? No water and some and half of water. Repeat.
It's like considering the equation of the
Well,
delta
I
F.
don't want the equation on what you heard. Okay.
I
Is there any
think,
difference about frequency?
in my opinion, we should heard a different decrease.
Have you tried this?
Yes.
Have you tried this?
Yes.
What you heard?
I heard doing water is still or
The
is
frequency. Is there any difference? The same or different?
is different.
Different. Higher or lower?
It's lower.
Lower. How about
Yes.
reported? How about reported?
Uh,
You know what my question?
Can you repeat again?
Okay, the ball empty and the field half of water, and you hit the ball. Is there any difference?
You mean with-
Sound, what you heard the sound, is there any difference?
You want to ask if the water is higher or lower?
No.
What's that?
Empty and half water.
It's empty and half water.
Yeah. You hit the ball, you heard something, okay? You feel the beating.
With the empty one, it's kind of higher because the air
Okay.
air balance.
How about the viewer?
So I would try that. I would try to strike the empty ball and the ball that added water. So the ball that without water will have a higher intensity and it will not have the humming sound. Like it will have a light sound, and the frequency is higher.
Have you done this experiment?
Yeah.
You heard that?
Yeah.
Okay,
And
what's the
when,
difference?
yeah, it's
So
a
the
obvious
frequency is
difference.
higher or lower? Which one is
When
higher?
added water, the frequency is lower.
Okay.
Yeah.
Okay, thank you.
Thank you.
Now we go to the storing section. So let's go to the storing section and we start from the composer first. Please raise your grade. 48555. And the pollen is 47444. And reviewer, please. 67877. Looks quite consistent. So, Eva, do you want to say something? Yes, please.
Just a short suggestion for reporter. So the figure presented, each axis shows a clear name with X, that was units, and no abbreviation, no twist. So it's better for presentation, it's a citation.
Okay, thank you. So, let's also take a 50 minutes. Okay, 15分钟的 break。但是呢，麻烦还是请你先移到下个位置，check 你的电脑 OK。